What's going on, everybody? Johnny Bannon here, the networking guru, and today we're doing part 2 of our Security Plus crash course. And in this section, we're finishing up Domain 1. Yes, I had to split it into two sections because even though Domain 1 is not so much information as far as like the exam objectives go for percentages, when I talk about encryption, I feel like I need my own video for it. So finishing up our last section of Domain 1 is going to be Domain 1.4, which is pretty much public key infrastructure and encryption, levels of encryptions, cryptography tools, and that takes a while to explain. It's a deep topic. In this video, we're not going to dive into the history of encryption and all this stuff that you may see on other videos because this is a crash course. We just got to get to it. We're going to jump right into it. What encryption is, PKI, cryptography tools. So let's do it. Don't forget to like and subscribe. Okay, so Domain 1.4, explain the importance of using appropriate cryptographic solutions, and we're gonna jump right into encryption algorithms. So you can see finishing up Domain 1, we gotta go over encryption, we gotta go over public key infrastructure, PKI components, and then we're gonna finish off by going over cryptographic tools. So jumping right into it, let's just define what encryption is. So remember, this is a crash course, so sorry if I don't give an hour lecture on encryption. So this is, simply put, the process of converting information or data into a code that's unreadable. We describe this as turning plain text into ciphertext. So when I send data across the wire, my computer is talking to my switch or my router or a web server, and I'm looking in that wire. Let's say I can look inside that wire. If I'm sending that data without any encryption, it should be human readable. I can see the data coming across, I should be able to read it. Well, with encryption, that's not the case. When we encrypt that data, whatever that data may be, we change that human readable plain text into something called ciphertext. That ciphertext is unreadable. Now, what is that process of converting plain text into ciphertext? That process is called encryption. We essentially use an encryption algorithm along with a key, so it's two parts, an algorithm and a key. The key, activates the encryption to encrypt data, and then it deactivates that encryption with decrypting the data. So it's two. Encryption is really two parts. The encryption algorithm, which there's a lot of different ones, a lot of different standards for it that we'll get into. Two major types of encryption too, symmetric and asymmetric. So we have the algorithm, and then we have the key. Think of the key as exactly how it sounds. How do you unlock and lock a door? With a key. How do you activate, deactivate encryption? To encrypt and decrypt? With a key. Now, the longer the bit key length of that key, the stronger the encryption. There is a little bit more to it than just a simple analogy of a door and a key, but that's essentially it. So when I want to turn plain text into ciphertext, I encrypt that data, whether it's data in transit, data at rest. Encryption does the same thing, right? Makes something not readable by changing it into ciphertext. Now, when it comes to Security Plus, as cybersecurity engineers, we use encryption for a lot of things, for confidentiality, to confidentiality is the main point, right? You think of the CIA triad, but it's used all the time. It's used all the time when we're in an untrusted environment with our data in transit and with full disk encryption on like our hard drives or our storage area networks. So to finish off this slide, right, it uses an algorithm and a key to transform readable data, known as plain text, into non-readable format, known as ciphertext. The key is a piece of information or a sequence of bits used by the algorithm to perform the encryption. Okay. Now moving on. So why? The why. Why do we use encryption? I was almost getting ahead of myself. So I have all the listed points here that the reasons why we use it in security and IT and on the network. So confidentiality, it ensures that sensitive information remains inaccessible to unauthorized individuals, people that don't have the key to decrypt and encrypt. Authentication. So when we talk about asymmetric encryption, we use the public key cryptography to actually authenticate. We use asymmetric encryption to create digital signatures, which we'll learn about, which give us non-repudiation as well, but also authenticates that the sender is actually the person who sent the message when they add their digital signature, and that requires asymmetric encryption, so we have authentication. And then, of course, non-repudiation. Also, then, on a bigger scale, right, not the why, like back in the 80s, why they invented encryption, because they wanted to see to make it ciphertext, right? But there's now in our modern era, with all these different sectors and industries that require data governance and compliance, encryption is mandatory in a lot of these. So like in the DoD, where I come from, we have something called NSA or NIST standards that require certain levels of encryption. Other industries have things like HIPAA, if you're in the healthcare industry, require certain levels of encryption. I'm sure PCI compliance, which dictates credit card transactions and credit card processors have to be in compliance with PCI. I'm sure they have an encryption standard that we have to adhere to. So we use encryption for compliance in our industries. Okay, now to talk about the first type of encryption. So we're just going over encryption and exactly what it does. We'll later get into how this works with PKI and how we browse the web securely. That's kind of the whole point, I think, of this section, to kind of learn public key infrastructure. You got to learn encryption first and where we apply encryption. And of course, it doesn't always correlate to PKI. We could have VPN, IPsec tunnels that use encryption. So understanding these fundamentals helps us understand a lot of different technologies that help secure things. But the first encryption we're going to talk about is symmetric encryption. So there's two major types though, symmetric and asymmetric. We're going to start with symmetric because it's the easiest to understand when just learning encryption. So the key thing with symmetric encryption is, well, it's a couple key things. One, there's only a single key, a shared secret key that's used for both encryption and decryption. So when I'm a sender and I want to encrypt a message, I use my key to encrypt to activate that encryption algorithm. The receiver has to use that same key to decrypt. So the sender and receiver must both have access to the secret key and keep it confidential. With symmetric encryption, it's also efficient. When we want to encrypt bulk data, when we actually get down to like the TLS sessions we do from from client to web server, it's going to use a symmetric encryption to actually encrypt all that data in transit. There's the algorithms that we're going to talk about here in Security Plus is AES and DES, because that's what's on the exam objectives. There's other types of symmetric encryption though. But then use cases, yes, symmetric encryption is often used for encrypting large amounts of data, such as database information or files on a disk, and also for those big data in transit, connections. So it's not as resource intensive. Okay, so how does it work? So with symmetric encryption, we have our sender here. So Amanda wants to talk to Steven. That's going to be our destination or our receiver. So she has a plain text message. She's going to use a symmetric encryption algorithm like AES, and she's going to have a shared secret key. She's going to use that shared secret key and that AES symmetric encryption algorithm, and I'm just saying AES as an example, to then encrypt that data to change it into ciphertext. She's then going to send that message over to the receiver or to the destination, Steven, and now she has to figure out a way to somehow get this secret key over to Steven securely. And Steven's going to use that same key to then decrypt and see that plain text message, and now it's human readable. So hopefully you saw in that process, right, what could be the issue here? Let me get my pen application up. So what could be the issue with symmetric encryption? We know it's used efficiently, right? So when we're doing that bulk encryption, we want to use it. But what's the problem here is that Amanda's key, how do we get it over to Steven securely? Now you may say, oh, maybe they're directly connected to each other on the same switch, and it's just the private key that was generated when we started using AES, we just sent it an email directly or handed it to Steven on a USB. We could say that, but that's not how the internet works. That's not how the network works. When you're talking to people, they're not always right next to you, and you can give them a USB to install a private key. So if she was in Arizona and he was in New York, we have a problem. How did we get that private key over to Steven in New York through an untrusted network like the internet? Well, that's where asymmetric cryptography comes into play and secure sharing key algorithms. I think I said that right. Things like Diffie-Hellman and elliptic curve cryptography and really asymmetric encryption. Asymmetric encryption, which we're about to learn about, fixes this issue we have where these shared secret keys that we need for symmetric encryption have to be sent securely. And we're going to go over that. Before we go over how asymmetric encryption does that for us, we have to describe asymmetric encryption. But key takeaway here is you see the issue here. We have to securely exchange this key. So we have to use secure key exchange algorithms. That's the proper term, secure key exchange algorithms. Okay. So there's the full flow. And there's without the arrows being distracting. Okay, so now on to asymmetric encryption. So asymmetric encryption, also known as public key cryptography. This involves two mathematically related keys. And really, guys, when we talk about public key cryptography, a lot of times people say, no, only the public key encrypts and private key decrypts. For our public key infrastructure, that is true. Getting a little ahead of myself. But I want you to understand is when we use an asymmetric encryption algorithm, like a basic one like RSA, which is used for like SSH, right? Well, it's used for a lot of things, but learn about in PKI, or like ECC, elliptic curve cryptography. When we initially generate that public and private key, it's arbitrary which ones are selected. They're mathematically related. So if I encrypt with one, I decrypt with the other. It does not matter. If I encrypt with the private, the only thing that can decrypt is the public. If I encrypt with the public, the only thing I can decrypt with is the private. Those are mathematically related. If I encrypt with the private and I try to decrypt with the private, that ain't gonna work. That's not how the public key cryptography works. These are key pairs that are mathematically related to each other. Now, I'm not a PhD in math. Maybe you don't have to be a PhD. I don't know how that exactly works, but I just know that's how it is, right? One encrypts, other decrypts. That's how it's going to work. Now, the public key can be shared openly, though. So now the beauty of asymmetric encryption that solves the issue with symmetric encryption is that public key can be shared openly. Now, you may say, well, isn't that insecure? Well, the way it's supposed to work is whichever key is designated as public and private, now they have their roles to play. So the public key can be shared. It can be globally shared with everybody. Certificate authorities, the website's X.509 certificate we're going to learn about. The public key's for everybody. It's for the streets, it's for everybody. The private key, though, you got to keep that safe inside. That's inside your house. Ain't nobody in that private key. That private key is kept secret by the owner. When we say owner, when we deploy a web server, a website, and we need HTTPS, we need to use asymmetric encryption, so we generate public and private keys. The private key stays on our web server. No one should be able to access it. And if it ever gets exposed, you're done. Regenerate, get a new SSL cert, because that cannot be exposed. The private key is always kept secret, okay? So when is asymmetric encryption used? It's used for secure key exchange. It's used for things like digital signatures, which we're going to learn about, and encrypting small pieces of data like passwords. And really, what we're going to talk about here is how asymmetric encryption does secure key exchange and digital signatures. But before we get even to that step, let's go over just how it works. So let's say we were using asymmetric encryption to send an encrypted file, an encrypted message from Amanda to Steven again. So let's say, again, I'm just going to write this up here just so it kind of makes a little bit more sense. We're using RSA. So both Amanda and Steven are using RSA to send encrypted messages to each other. So with RSA, since it's an asymmetric encryption algorithm, asymmetric cryptography, they're going to generate what? Key pairs, a public key and private key. Their public keys are for everybody. I'm going to draw a globe here, right? Can I draw America and South America from memory? That's kind of what it looks like, right? But this is the globe, right? It almost looked like I drew another key. Let's see, Africa. I drew a better Africa, I feel like. But it's for everybody, right? Those public keys are available to everyone. And Steven's public key, if I'm like an attacker, right? So I'll draw an attacker here. Frowny face. If I steal that public key, right? Here's Steven's public key. What good is it? It's not stealing, it's available. What can I do with that? Nothing. If I encrypt Steven's public key, what's the only thing that can decrypt? The private key, which guess what? Those private keys stay local. They don't go anywhere. They're supposed to stay on that computer. So unless I go to Steven's computer here, I say, hey, Steven, let me get on that computer. He gives me root access and I get into the folder, the hidden folder that is storing the private key, and I take that thing. The public key is for everyone. It doesn't matter, right? And that's the beauty of it. If that private key is kept secret, those public keys can be available for everyone. Okay, so moving on, I'm going to make those arrows again and make sure we understand the private keys stay there. Okay, so here's how we encrypt, though. Now, when Amanda, the sender, needs to talk to Steven, the receiver, and use asymmetric encryption to encrypt the message, guess what we're going to use? We're going to use Steven's public key to encrypt. You may say, why not use our public key? Well, what good is that going to do if I encrypt the message with my public key and send it to Steven? There's no way he can decrypt it, because guess what? The only thing that can decrypt is the private key. Now, rephrase that. If I encrypt with one key pair, the only thing that can decrypt is the other key pair. So if I want to send an encrypted message to Steven, our receiver, I go grab his public key, and boom, I encrypt. I send that message to Steven. He notices he has an encrypted message, and we know we're using RSA. So he says, okay, well, if I'm getting an encrypted message from using the RSA algorithm, there's only one way I can decrypt it, with my private key. So then he's gonna decrypt this private key, and there's that plain text message. And that is entirely how asymmetric cryptography works. Now, before we move on, you may say that's good and dandy, but why don't we just screw symmetric? Why don't we just do this all the time? It seems way more secure. Because asymmetric encryption is not efficient for sending large amounts of data. And the beauty of asymmetric encryption is that the process you just saw here, we can use this process to then create a unique shared secret key between our sessions here that no one else can use. You may say, what are you talking about? Okay, so check this out, guys. I'm going to skip ahead of my slides here. So imagine we're in like a silo here, right? We're in our own little silo. And when you're doing client to web server architecture, it is kind of like that. When you're doing HTTPS, you're on your own little TCP data channel in your own little session that's connected end to end, right? So we're in our own little silo here. So how can we use our public-private key pairs to create a new shared secret key securely to use for symmetric encryption? So here's how it works. Using asymmetric cryptography and a secure key exchange algorithm like Diffie-Hellman or ECC, here's what we do. The goal here is that we're going to use asymmetric encryption to get to our end goal of using symmetric encryption. Now, why is that our end goal? Because that's more efficient. That's for encrypting bulk data when we're sending gigabytes across the network, right? Or across the internet because we're downloading a video game or an ISO file, whatever the case. So here's how it works. My private keys have to stay local. We know that. They're not going to go anywhere. We're not sending those anywhere. What we can do, though, is I can take Steven's public key and combine it with Amanda's private key. And that's going to create a new shared secret key. There's our new shared secret key. I should have put the shared on top. You understand. And then as Steven, I can take Amanda's public key and combine it with my private key. And then I'm also going to create a new shared secret key. And through the beauty of a math that I don't really understand, because I can't dive into those algorithms right now in this video, these secret keys that were just created from Steven taking Amanda's public key and combining it with his private, and from Amanda taking Steven's public key and combining it with her private key, we just created two new shared secret keys that are mathematically related to each other. And nobody can go grab that shared secret key, right? Because they're not in this little silo here that I drew up with our asymmetric session. So when you think about a client to web server like TLS, now this is just very simple. It's not describing the whole TLS handshake process. If the goal is to have an encrypted TLS session, if we start our session by doing asymmetric cryptography, then do secure key exchange using asymmetric encryption, that's going to create a new shared key that we can then use to do symmetric encryption, and nobody can steal the private key that is being used for symmetric encryption because it was created from this process. So step one, asymmetric encryption, that creates a new shared secret key that's unique to our session here between Amanda and Steven, and then we use that for our symmetric cryptography. That's how it works. That's how we can use asymmetric cryptography to do secure key exchange between end-to-end client to web server to do symmetric cryptography. Now, if that didn't make too much sense, on this slide I have an example of shared secret key exchange using Diffie-Hellman, and you can see it's doing the same thing again. Alice and Bob here, we have some different names, but Alice has her private key, Bob has his private key, he has his public key, and Alice has her public key. Alice is going to take her private key and Bob's public key and create a new shared secret key. Bob will do the same thing. He'll take his private key and Alice's public key and create a new shared secret key. And through the power of math, you see that little algorithm there, the power of that algorithm that I don't want to describe because you don't need that to pass the Security Plus exam. they create a new shared secret key that can be used between them. So now it's going to allow those two parties to generate a shared secret key over an unsecured communication channel that no one can go intercept, right? Awesome. ECC does the same thing. Just a definition of ECC real quick. ECC is a form of public key cryptography based on the algebraic structure of elliptic curves over finite fields. Just memorize that algorithm, okay? That acronym. Okay, so shared secret key exchange, just to define it more. In both Diffie-Hellman and ECC, the shared secret key is derived from these exchanges is typically used to encrypt further communication using symmetric encryption. This approach combines the security of asymmetric encryption for key exchange with the efficiency of symmetric encryption for data transfer. Those steps, asymmetric, secure key exchange, symmetric encryption. That's the steps we get. Now let's go over some of these algorithms. So take a little breath, right? Now we went through all that, and now we can get down to some memorization for our Security Plus exam. So the first symmetric encryption algorithm we're going to talk about is DES, or triple DES, which is just DES 3 times, okay? So this was one of the first symmetric encryptions that is now obsolete, okay? It has slower performance, and it's not as secure as AES, but it's one of the symmetric encryptions we're going to learn about. So on the exam, kind of think of just triple DES as an older, weaker symmetric encryption algorithm. Next, we're going to talk about RC4. So RC4 is a stream cipher that generates a pseudo-random stream of bits. I'm not even getting into that. It's another symmetric encryption algorithm where its key ranges range from 40 to 2048 bits. It was historically used in older protocols like WEP, but now it's vulnerable, okay? And it's also been replaced with AES. That's our standard now. AES is the go-to standard for symmetric encryption. It uses the same key for encryption, decryption. It's a symmetric key algorithm. It was established, the NSA, right, or NIST, the U.S. National Institute of Standards and Technologies. And it was the successor to DES, the data encryption standard, or triple DES. And its bit key lengths, or its key sizes, are 128, 192, and 256. Obviously, the longer being the better. We don't have to go into and deep dive how these encryption algorithms work. You just got to understand they're symmetric and that they use a single shared secret key. If you want to deep dive, there's plenty of trainers that'll deep dive into how these algorithms actually work. For the Security Plus in this crash course, it's not really needed. Some asymmetric ones, RSA, that's probably the most popular. If you ever generated SSH keys, that's using RSA. So RSA algorithm is based on the mathematical difficulty of factoring the product of two large prime numbers. Very cool. We don't need to dive into it again. Just know that RSA is an asymmetric encryption algorithm. All right. So that was the fundamentals of encryption. Now let's move on to the different levels of encryption. Okay, we're here. So now let's go over the different levels of encryption. This will be a little bit quicker than our previous section. So we're just going to go over where we can apply encryption now. This is kind of going to be going over more the data at rest, but we will also look at data in transit of where we can actually apply that encryption. So, diverse levels of encryption. So encryption can be applied at various levels, each serving different security needs and scenarios. So full disk, partition, file, volume, database, and record encryption, that's kind of like our data at rest. But also I have down here a little SSL symbol, our data in transit. We can do IPsec encryption as well, or IPsec tunnels that use encryption. Okay, so securing data at rest, full disk encryption. So full disk encryption encrypts the entire hard drive, including the operating system. So think of BitLocker, where you have to put a pin before you actually go through your boot process to bring up the operating system. This is the best way to really protect your devices when it comes to securing the entire drive, right? So it protects data at rest from unauthorized access, and especially in cases of theft or loss. We have file and volume, so targeted encryption. So maybe we don't want to do full disk, maybe we just want to boot up for whatever reason. Well, we can do both actually. We can do full disk encryption and then still on our device say, hey, I'm going to encrypt this single file, give it a password, and until you put in that password, I'm not going to decrypt it. Or volume. So let's say we make a C drive, a D drive, and an E drive. In our C drive, we're not going to encrypt, but we encrypt the D drive. So that's volume encryption. Okay, ensuring secure data at transit. I don't have a slide up here, but we also need to go over record-based encryption and what was the other one? And database encryption. So imagine like a SQL database, right? Where we have all these tables and each maybe row and column, we consider that a record. So we can do an entire database encryption, whether it's SQL, NoSQL, MongoDB, any kind of database you may have. We can encrypt that entire database, or we can encrypt certain records. Very similar to how volumes and files function, where I can have a volume that's unencrypted, but then I can have files in there that are encrypted. Or I can encrypt an entire volume and also encrypt the files in there. So it's not like a one or the other, it's just different levels at which we can secure things. Ensuring secure data in transit. So when data is going across the network out to an untrusted network like the internet, we can secure it using things like IPsec tunnels, TLS, like HTTPS sessions, which we're about to get into when we go over PKI. But that uses encryption, okay? Understanding algorithms and key length. So we kind of went over the different algorithms, symmetric versus asymmetric, with AES and DES being what? Symmetric. I hope you answered that correctly. You on the screen or you out there in your computers. And then RSA and ECC is what? Asymmetric encryption. That's right. I know you memorized that. And what they all have in common is the longer the bit key length for that key, the stronger the algorithm is going to be, okay? All right, that was easy. Now let's go into the public key infrastructure. Okay, we made it. So now we're going to be going over the public key infrastructure. So let's begin. And here's where we start. A bunch of images that I have to fill out and explain now. Before this, I'm going to go to my whiteboard. So let's transition over to my whiteboard. Okay, so I got rid of my face for this because I don't want it to get in the way. So let's check out what we got going on here, guys. So what is the entire point of public key infrastructure? So when I go to a website, so let's bring up Google Chrome, and let's say I go to google.com. Well, I went to google.com via something called HTTPS. Oh, that's right there. Okay, HTTPS. So that's the Hypertext Transfer Protocol Secure. So that S ensures that we have end-to-end protection. So if I were to look at this on the wire, literally let's do that. If I look at that on the wire, this session out to google.com, if I did a packet capture on my Wi-Fi NIC, my wireless NIC, okay, yep, there we go. And we paused it and then just looked up TLS. This is what we look at. That S right there means we're using the transport layer security, and it's HTTP Hypertext Transfer Protocol. And look, there's my encrypted application data. So in there's an HTTP probably like GET request, and there's probably a return code, right? Like HTTPS return code, like a 200 code saying okay, but we can't see it because guess what? We are protected using TLS. That's what that S means. So somewhere there's web servers that are hosting google.com that are saying we're allowed to do or they're allowing us to do TLS sessions to it, encrypted sessions to it, from end to end, from my device here, my computer here, all the way to google.com. So when now we go deploy a web server, yes, quit without saving, quit. When we go deploy our web server, so we go out and buy the domain name, let's say, I want to just make it easy, f.com. No, I don't like that. Not f.com. Let's make it something else. We'll give it a different name. Name it z.com. So there's our domain name, z.com. We went out and purchased this domain name. And now here's my web server, and I want to make sure that we have secure connections. I want to make sure that we are doing secure connections for all of our users. So when our users here want to initiate a HTTP session here, that is protected. So I want that secure lock icon on my screen. I want to be able to do HTTPS. Well, to do that, TLS requires what's called asymmetric cryptography, which we learned about, symmetric cryptography, and an X.509 certificate that verifies that we trust our public key and that we can do this TLS session and that we trust it. So how do we accomplish that? We accomplish that using the public key infrastructure. So the first step in using HTTPS on our web server is I have to go do what's called an SSL enrollment process or an SSL certificate request. Or, yeah, that's all the names I'm going to use, okay? So on my CLI here, this is the Linux web server, I go into my bash terminal, and maybe I do an open SSL request. That open SSL request is going to generate me a public key and a private key using our asymmetric cryptography, using RSA or ECC. That's something that you define. And then we're going to tell it, hey, create what's called a CSR. A CSR is called a certificate signing request. That certificate signing request is going to have our public key, and it's also going to have a bunch of other information. It's going to have like our canonical name, our domain name, our location, our country code, our state, a bunch of information, right? And in that certificate signing request, the most important thing is that it's also going to have our public key. So that certificate signing request is our SSO request, off to what we call certificate authorities. These certificate authorities are the trusted third-party providers that stamp our SSL cert, which we're going to learn is called X.59 certificate, that stamps it as trusted. And then baked in to your web browsers are going to be the certificate authorities that are trusted. So the developers that make Firefox, Brave, Chrome, Edge, bake in the root CA's public key or certificate and say, we trust these major certificate authorities. So this one's going to be DigiCert. That's a major one, okay? So let's go through that process again. Because remember, the end goal here is to do that HTTPS sessions. We want that lock icon. To get that S, we need to do TLS with all the clients that connect to us. To do that, we need to get an SSL certificate. And to do that, we need to go request to get an SSL certificate from a certificate authority. I'm going to stop using the term SSL certificate now because I'm going to change it to what it actually is, an X.509 certificate. To do that, we have to generate a certificate signing request. To generate a certificate signing request, we have to use an asymmetric cryptography algorithm to create a public key and private key. That private key then is, like we've already described, going to stay local. It's going to stay in our web server. That public key is going to be attached to the CSR along with other information that we want in our X.59 certificate that we're going to get issued to us. Things like our domain name, canonical name, subject alternative names, our location, our country, our state, and then of course our public key, because that public key is going to be what all of our users use to initiate encrypted sessions to us. Whew. Let's do it. So the first hop in that CSR request, or that certificate signing request, is first to a registration authority. That registration authority is going to just pretty much be the bouncer at the club saying, let me just check some things. Is your DNS blacklisted? No. Okay, everything checks out on this CSR. And then it's going to push us over to what's called the intermediate or issuing certificate authority. This certificate authority gets its authority from the root CA, okay? So we're going to get there. So this will be the issuing authority. So when we go get our X.59 certificate, once we receive it, that's going to be our issuing, and then that issuing certificate authority or intermediate is going to be pretty much approved by the root CA, okay? So this could be like cloudflare.com. And there's this trust between them that we call the chain of trust. Okay, so the registration authority takes our CSR, passes it off to the intermediate certificate authority. And there's already previously a chain of trust there, and we build that chain of trust, you guessed it, using public, private keys and digital signatures. We don't want to deep dive into that, but there is already that chain of trust. So the root CA is going to get our CSR. It's going to look over it. It's going to say, cool, now I am going to issue you an X.59 certificate. So it's going to respond to the issuing certificate authority and say, hey, you're good to go. I approve you issuing that X.59 certificate. And that issuing certificate authority is going to send that certificate back to them in what's called the X.59 certificate format. And in that format is going to be, again, our public key and also a digital signature from the root CA and the intermediate CA. This is the thing that pretty much gives us that non-repudiation that our X.59 certificate is from the root CA. Now, digital signatures also use the public key cryptography. It uses asymmetric encryption. So again, baked into our web browsers, we're going to trust DigiCert. And when we see DigiCert's digital signature on there, we're going to say, oh yeah, not only do we already trust DigiCert, but we just verified that you got your X.59 certificate from DigiCert and from that intermediate CA Cloudflare. So both their digital signatures are going to be on there, okay? Digital signatures are created by taking a hash So when we get that original CSR, right, we're going to hash it. And then using our private key, we're going to encrypt that hash, and that equals our digital signature. So I'm going to do it like this. That equals our digital signature. So you may say you encrypt with the private key, but I thought you always encrypt with the public key. Remember, I told you they're just mathematically related. So since we encrypt with the private key, and we have the root CA's public key already hard baked into us, that's how we validate it, right, guys? If I can decrypt that digital signature with DigiCert's public key, then we know that it had to be encrypted with a private key because they're mathematically related. So, perfect. So we get our X.59 certificate, and now we're able to do HTTPS sessions. So now hard baked into our web browsers is already that trust of DigiCert and Cloudflare. So when I initiate that TLS session, we do like a TLS request, right? Saying, hey, here I am, Chrome, here's my public key. They send us back their public key. We view their public key in their X.59 certificate. We do some checks on that X.59 certificate from the web server that says, oh, that's from DigiCert. I trust it. Let me verify digital signature, decrypt it. Okay, cool. Check the hash. Okay, cool. Decrypt Cloudflare's. Okay, cool. Digital signature. Check the hash. Okay, cool. We trust your certificate, Z.com. We trust it because you were issued it from Cloudflare and DigiCert, which we trust, and we just verified digital signature. So we know that you're good to go. Okay. So then we can do our encrypted TLS session. We do our TLS handshake. We use that asymmetric encryption to do secure key exchange. We create a symmetric, we use that new shared secret key to do symmetric encryption, and now we're good to go. So I'm not going to break down the TLS handshake. Pretty much it's like a TLS request, a reply, secure key exchange, and then we also define a TLS cipher suite that we're going to use. So before all this, like from web browser to web server, we decide, oh, we're going to use, SHA-384, RSA, and SALSA-20 for our encryption. So like RSA would be our asymmetric. Maybe we'll use Diffie-Hellman elliptic curve cryptography to do the secure key exchange. SHA will be all the hashing that we use to verify like digital signatures. And then SALSA-20 is going to be the symmetric encryption that we use to actually do our data in transit, okay? That is it. As simple as I want to make it for this crash course, the public key infrastructure. There's some stuff over here I want to talk about as well. Scroll down a little bit. Along with all this information on the X.59 certificate, along with the domain name, local country, a subject alternative name, things like that, there's also an expiration date. And those expiration dates and the certificate's validity, the validity of the certificate based on expiration, is housed in what's called a certificate revocation list server. And that certificate revocation list server is going to have every single expired cert on there, really robust. So if you ever want to verify whether or not a certificate is valid or not based off expiration date, you can download the CRL and check that way. Or you can use something more efficient here called OCSP, the Online Certificate Status Protocol, where instead of downloading the whole CRL list and looking at every expired cert, you can just send an OCSP request for a single domain like Z.com, okay? So that's also part of the public key infrastructure here. That's not part of all this process, but it's still a part of it to verify the validity of certificates. All right, now let's go back to our slides. So shake it off. I know that was a lot, but that was good. That was the public key infrastructure. And here's another little image I have of it if you want to pause and look at this image instead of my chicken scratch. Okay, now onto the slides just to kind of, confirm some of the things we just learned. So PKI hierarchy. So certificate authority is the trusted entity that issues digital certificates with authenticating content sent from the web server. So the root CA, that's the root certificate chain. Intermediate or issuing CA acts as the intermediate between the root CA and computers generating CSRs. Computers, but web servers, right? And that creates a chain of trust. We have a registration authority, which verifies that a user's request is valid by checking domain name identity, among other things. Pretty much just like, is this a bad domain? We don't want to issue a good certificate. And then the registration authority, like I said, is like that bouncer in the club that Once it's verified, you can then go to our certificate authorities. So certificate type. So don't get this twisted with the format that a certificate's saved in when issued. It's still X.509, but we have different certificate types. So wildcard certificate, let me minimize my face again. Hold on, there we go. This allows the organization to host multiple websites using a single key pair certificate. So pretty much I create trepatech.com, I do one certificate signing request, and I get a public key for trepatech.com, but I can still use that for all my subdomains called shop.trepatech.com or academy.trepatech.com. So we call that a wildcard certificate when it's able to be used for all of our other subdomains, okay? Extended validation, I kept this over from the old 601 exam objectives, but it's not on there, but we can read it. A type certificate that carries a high level of assurance. SAN though, subject alternative names. This is a multi-domain certificate. So there actually, in every certificate I've seen online, there's subject alternative names that pretty much represent that certificate for multiple other entities and domains. So if I open up Chrome again and I go to youtube.com, I'm gonna bring this into view. I go to youtube.com and I look at my certificate. I go to details and I scroll down here. Did I miss it? Certificate subject alternative names. This shows you all the other SANs that pretty much saying like, oh, youtube.com or google.com, googlecommerce.com can use this certificate, right, as valid, okay? So YouTube is bought by Google, right? So you may say, what the heck? But you see all the different just, .de, which is like Germany. I don't know what ES is. Spain, maybe? .fr, France. You get the picture though, right? So this is what a subject alternative name is, which is not youtube.com, right? But it's saying, hey, but this certificate can be used for all these other domains because it all belong to me at the end of the day, me being the organization Google. So when Google first created that CSR, in that CSR was all these other subject alternative names that got sent to the issuing certificate authority and the root CA, and they said, okay, all this is going to be part of the X.59 certificate that we give you. And this is the X.59 certificate, okay? Google certificate, the issuing certificate authority certificate, and the root CA's certificate. Now back to the slides. Okay, certificate usage, profiles, and templates, kind of just, again, hitting on what we've been over, client authentication. So instead of using a traditional username and password, certificates, like in an internal PKA infrastructure that's integrated into like LDAP and Active Directory, we can use certificate-based authentication rather than regular username and password credentials. Server authentication, so used to authenticate to legitimate servers to clients and encrypt the communication, literally what we just described, right? That's what certificates are used for. PKI concept, so a trusted provider. So a trusted provider or a trusted third-party entity or party is just a root CA that our web browsers trust. That's it. Because I could go deploy a Microsoft Windows CA, which is what I'm going to do in one of my videos that I'm going to make that's not certificate related, more SKU related. I can go make a certificate authority. But Chrome, standard Chrome that I install is not going to trust the root CA that I made in my bedroom, right? Off my little like hypervisor engine EXXI server. Of course not. So a trusted provider is the one's already baked into the web browser that's trusted. Cross-certification, this is when two or more CAs need to trust each other. They'll use their private keys to sign a certificate containing the public key of each other, and then they have cross-certification. A CSR, certificate signing request. So we kind of already went over this, right? This is the thing that gets sent to the certificate authorities and the registration authorities. Lifecycle management. So like we kind of already talked about, something that you have to be aware of if you're deploying web servers is that they will become expired, the certificates you request. Now this is typically done like automatically for you. Like if you're deploying a WordPress site, there's a plugin that probably will remind you yearly or in 3 months, your certificate's about to expire, whatever the case may be. But think about your lifecycle management, okay? Okay, OCSP, so again, that online certificate status protocol, like we talked about earlier, just another way to check the validity of that certificate. Much same thing the CRL does, but with the OCSP protocol, it's much more efficient, faster, because it'll let you just request for a single domain without downloading every single expired certificate that's on the CRL. And then certificate stapling, this allows the clients to trust a server certificate without contacting the CA for updated CRL independently. Okay, then here's what an X.59 certificate actually looks like. So you can see, like, maybe I'll do a demo too of using OpenSSL. It's like a free way to do your CSR generations, like on a Bash terminal or like a Linux. You can do it in Windows too, actually. But anyways, OpenSSL is like the technology that enables that. But here's what an X.59 certificate looks like. The point of me saying that is when you generate a CSR, it'll ask for all this information: your country, state, locality, organization, the serial number, like it'll be given to you, the common name. So what is the name of your website, right? Um, yeah, but here's all the X.59 attributes. All right, now let's go ahead and move on to domain 1.4.4. Okay, so now let's go over PKI components. So this is gonna be another kind of long one. We got to dive into what digital signatures are, hashing, kind of defining it more, and other cryptographic components or PKI components, really. Okay, so hashing. So what is hashing? So when I first started learning about encryption back when I was a Sec Plus student back in like 2015, 14, getting old. That was like 10 years ago now. But anyways, I always got confused between hashing and encryption because hashing always looked to me that it converted that input hello world to this digest. It's not converting anything. It's creating something new. It's creating a digest based off the original input, okay? Hashing does not equal confidentiality. Hashing equals something called integrity. Hashing is the process of converting input into a fixed size string of bytes, usually called a digest or checksum. Now, when we say converting, we don't mean plain text or ciphertext. We really mean creating a digest based off that original input. So when a hash function is applied to a piece of data, it produces a hash value or hash code, a digest or a checksum. And that digest or checksum correlates to that input. So with this hello world input, we ran it through SHA-256, as we can see here, and it created this digest. But if I did this again, but instead of hello world, I put hello world with a 0, and I ran it through the SHA-256, I would create a whole new digest. It would be a whole new digest because this digest is supposed to correlate to this original input. So that's how it verifies integrity, right? If I have these digests for hello world, and let's say this is a script, and then I download that script from a website, and then I get that script and I run it through locally now. I download it from a website. Now it's on my local machine. It's in my downloads folder. And I run that executable through a hash function again, and I get this digest that's different from this original one. I just verified that there is no integrity, that somewhere along the way, this executable was changed. But if instead I get the same digest, I know that's good to go. That's a thumbs up. I just verified integrity because here's the digest for this executable file that is posted on the website I'm downloading the executable from. I downloaded it. It's in my local machine now. It's in my downloads folder. I go to my terminal. I run that executable through a hash function, and it creates a digest that matches the original one that's posted on the website. That just verified integrity, and that executable was not changed. Now it still may be malware, right? But it hasn't changed, at least from the web server to my computer. Okay, so here's how you check a hash too on the terminal. Well, I have here the command prompt and PowerShell, how we check a hash, okay? So here, cert on command prompt, it's cert utility dash hash file. Here's the file we want to run a hash through, SHA-256, and here's what we created. Or here's the digest that equals that file sign.pdf. And then here's how we do it on PowerShell. The commandlet is get dash file hash. Okay, so different hashing algorithms. So HMAC, this allows a packet / data to be authenticated and have integrity. It will use a secret key known by both the sender and receiver to create a unique message authentication code. So it's the same thing, but we get authentication as well as verifying integrity. MD5, that's a hashing algorithm that's deprecated now, that's insecure. RIPE-MD, also another family of hashes. It's not used in the government or really commercial use. It's not necessarily deprecated, just not really widely used. Then we have SHA. That is kind of the standard. And SHA is a hashing algorithm. And the bit key length, the longer it is, the stronger the hashing algorithm is. Similar to an encryption algorithm in that way, but again, they're not the same. But here's the different SHA standards we have. So we have SHA version 1, 2, and 3, and then the different bit key lengths for that hashing algorithm or the message length. Okay, salting. So salting is a method to enhance the security of hash functions, particularly in the context of storing sensitive information like passwords. So let's think of something here, guys. Okay, let's say we have a database that hosts our usernames and passwords, and we hash the password. So instead of putting the actual password in there, we put the hash of the password in there for protection. So let's say we know that password, when we put it through SHA-256, it's always going to create this hash. Always. So we know that as an attacker. So then I look at a file like the etc shadow file on Linux, which hosts all the passwords on that device, on that Linux server, and I see SY0-701. And I know that this shadow file is also using SHA-256 for all of its hashing. Well, guess what I now know? Now I know what the password is, because I know that FE02 equals that. So we have like these, what is it called? Don't quote me on this. I'll put this in editing. I think it's called the rainbow table attack, or that's exactly that. We look at all the hashes for well-known passwords. So that's a way we can kind of, we can exploit that. So you may say, well, how do we get around that? If one user's password is password and the other user's password, their hash is always going to be the same. The hash is always going to be the same. That's a vulnerability. What we can do is something called salting, where we add random data to that password, and we know that's the salt that we add, that little salt that we added, and instead of getting this hash, we get a unique one. And then if another user decides to do the same password, we'll add a salt on there. There's our salt. Put it through SHA-256. And then guess what? We're going to get a unique hash. So not only does this prevent against rainbow table attacks, it prevents also against collisions as well. Something different than what I just described. Collisions is something where we use like MD5, which is not vulnerable, and we have this input and this input, and it accidentally creates the same hash. That's called collisions. If we add a salt to that, there's our salt that's added, which is just random data, we don't get that. We don't get that collision either. So salting just enhances the security of our hash functions, okay? All right, digital signatures. Now let's talk about digital signatures. So for the CompTIA Security Plus exam, know what a digital signature provides us. It provides us integrity, it provides us authenticity, and also non-repudiation. When a digital signature is attached to a message that gets sent to us, we can verify that it actually is the sender who sent it and that it also wasn't changed in transit. Here's how digital signatures do that. We use asymmetric encryption and also hashing to create a digital signature. What we do is we take data, we create a message digest from there using a hash. Once we get that message digest, we're going to take the sender's private key and encrypt that hash, the digest, right? Encrypt that message digest. And then that creates a digital signature that we attach to that document. Once it goes to our receiver, if the private key encrypted, what's the only thing that can decrypt? The public key. So if we're able to take the sender's public key and decrypt that digital signature, we just verified that it was the sender who actually signed it. Why? Because the sender's private key, if it encrypts, the only thing that can decrypt is the sender's public key. So if we're able to decrypt with the sender's public key, we know, oh yeah, that is from the sender, because I just decrypted something with his public key. That means it had to have been encrypted with the private key. And then we get the original message, right, and the hash. We're going to run that message through the same hashing algorithm again locally and compare the original hash to the one I just made. And if they match, I just verified the integrity. Whew. Now let's look at it like this. So how do we make a digital signature? So Amanda here wants to send a message. Howdy, partner. She's going to send that message through a hashing algorithm. From there, we're going to get that digest. So here's that digest, okay? Now, I know you need to change this because hashes usually are like hexadecimal. They don't have S's in there, so that's something I need to change that people have left comments on before. So I know I should have changed it before I started the video, but these slides have been made for a while. Okay, but as long as I recognize it, right? So here's the hash of that plain text message. Now remember, this is not encrypting anything. A lot of times people get confused. Digital signatures don't encrypt nothing. All they do is verify what, guys? Authenticity and integrity, which also gives us something called non-repudiation, which means we can verify who sent it. We know who actually sent it. Okay, so we take that original message, put a hashing algorithm to it, SHA-256. That creates a message digest. We're then going to take the sender's private key, because in this scenario, we're working in a public key infrastructure, right? Where the sender has public-private key pairs. We're going to take the sender's private key. Well, the sender's going to do it, right? The sender's going to take its private key and encrypt that digest. Once that digest is encrypted, that's called the digital signature. And we attach that digital signature to the original message, which is still plain text. I just always point that out. It's not encrypting, right? We send that digital signature to the receiver, Steven. What Steven's going to do is say, oh, there's a digital signature attached to this from Amanda. That's Amanda's digital signature. Well, if that's Amanda's digital signature, I should be able to decrypt that digital signature with the public key. Steven's able to do that with Amanda's public key, so we just verified authenticity and non-repudiation. Dope. I know that it was Amanda who sent that. So now we're left with the original message digest. So we're going to take that digest, put it off to the side. Steven's then going to take that original message and run it through the same hashing algorithm again. He's going to get his digest that he created locally and compare it to the original hash that was sent from Amanda. And if they match, we just verified our integrity. So now through the use of digital signatures, we have integrity, non-repudiation, and authenticity. All right. Last thing we're going to talk about here is something called key stretching. So key stretching is a technique used to enhance the security of passwords or cryptographic keys. It involves taking a potentially weak key or password and processing it in such a way that it becomes more secure against brute force attacks. Some of the ways we do this is with BPKDF2, which uses SHA-2 hashing and a salt of at least 64 characters to protect passwords. So that's already like our enhanced hashing, right? It uses a hash and salting. And then also bcrypt, very similar. It allows for key stretching, but it uses a different cipher. Bcrypt uses something called the blowfish cipher, but it could use SHA-2 as well. But anyways, key stretching, these are two key stretching algorithms that use hashing with salting to just give us an enhanced hash, okay? That's what key stretching is. Awesome. Now let's move on to our last section of Domain 1 in the Security Plus crash course. Okay, so Domain 1.4.5. Explain the importance of using appropriate cryptographic solutions. We're going to go over cryptographic tools. So this is our last section, so it'll be a little quicker. We're just going to go over tools that allow us to do cryptography. The first thing we're going to talk about is a TPM or TPM chip. This allows us to verify firmware and authenticity. It does this by taking a hash of the OEM, the original equipment manufacturer. So think about a motherboard. Think about all the firmware, all the pieces of hardware on there. We get a hash from the first time it boots up. We store that hash in the TPM. Then every single time after that we boot up, we get another hash compared to the original hash in the TPM. And if it's good to go, we just verified that none of the firmware or hardware has been changed. It could also be used in something like full disk encryption, secure email, and software licensing. It just helps us verify integrity. Boom. An HSM, a hardware security module. This is a physical device that provides secure generation, storage, and management of cryptographic keys. It's a dedicated appliance for large enterprises that are doing large rounds of encryption to manage the keys and to manage that encryption. So it's widely used in data centers and enterprises for managing SSL and TLS keys. Imagine you have millions of users hitting a web server, right? And managing all that TLS cipher suite and encryption, banking, financial services for secure transactions, a dedicated encryption appliance. KMS. This is like, really this is just a key, a password management database, but they want to call it key management system. That's fine. So this is a software that centralizes management of cryptographic keys for organizations. On the screen here, I have something called KeyPass. That's what we use when I say we in my personal company at work to manage all the different passwords and encryption keys we may have, right? It's really just passwords, right? Key management system. Okay, Secure Enclave. A secure enclave is a dedicated chip in a device like a smartphone or computer that provides advanced security features by isolating sensitive operations from the rest of the device, kind of like almost sandboxing or running things in your secure enclave away from the rest of the system. This could be used in like your BYOD deployments when you have a corporate phone that allows you to have personal things on it. You can do something like a secure enclave. So it is commonly found in modern smartphones and tablets for securing biometric authentication and mobile payment information. Also just for maybe doing things like Apple Pay, right? I had to go to speech therapy as a kid. Don't make fun of me when I mispronounce this. Obfuscation in cybersecurity refers to the practice of making something difficult to understand or interpret. It is often used to protect software code from reverse engineering or tampering. Steganography. So steganography is the practice of hiding messages or information within non-secret text or data. So pretty much think of an image, and in that image we're hiding little text or code. Tokenization. If you use Apple Pay or Google Pay, you use this all the time. So tokenization is a process of substituting a sensitive data element with a non-sensitive equivalent, known as a token. So pretty much instead of sending your credit card information across the wire, maybe we send a token that goes to the banks, and then that bank has a database or server that correlates that token to your user, to your PNN, right? Your personal number, whatever. I forget what the term they actually called, but your credit card number essentially, right? So it just replaces that sensitive data with a token. Data masking. So data masking, also known as data obfuscation, involves hiding original data with random characters or data. The data remains usable for purposes like testing and training, but is protected from exposure. So just kind of obfuscating some bits, pieces of data, maybe on a file or a database. All right, so that is the Security Plus crash course for Domain 1. I want to thank everyone for viewing, and what I'm also going to attach to this video is our Domain 1 question videos that I made, pretty much going over a bunch of Domain 1 questions. So that'll be also available in the next section. So stay tuned for us going over those videos. Thank you for viewing, like, and subscribe. Let's zoom in here, and let's go ahead and get started. A company places fake confidential files on its servers to detect unauthorized access attempts. If a cybercriminal opens one of these files, security teams receive an alert. What type of deception technology is being used? So all four of these are deception technologies. Specifically, it's asking about files. So files on its servers. So two options already stick out to me: honey file and honey pot. Honey token would reference like a token, a fake token for like web authorization or something like that. That's not what it's saying here. And a honey net would be a fake network that's trying to emulate the real production environment. What we're talking about here is just fake files on its server. So it's going to be B or C, a honey pot or a honey file. So more accurately, probably this one's going to be a honey file. A honey pot would be like a fake VM. A lot of times you can do this like in the cloud environment, put up a honeypot VM, see it get exploited in a nice little contained environment if you want to do this at home. But yeah, it's a honey file. Pause the video if you'd like to read our explanation here. Question 3. A security administrator configures a system where employees can only access files and systems necessary for their job roles. Which authorization model is being used here? So this is part of like our identity access management. And these are just pretty much in an organization, a policy saying, hey, if we go with role-based access control, we're going to give you permissions based off what you're doing for our organization, your role. Mandatory access control is going to be based on a need to know. So do we have different classified systems? Do we have sensitive, public, confidential files or networks or entire ecosystem? And if you have a need to know, you'll get access to. Discretionary access control, that's going to be where the owner, so let's say like a Windows system, this is the default access control method. If I create a file as the owner, I then give the read, write, and execute permissions to that file. That's discretionary access control. So whoever created the file, the object, will then delegate the permissions. Then attribute-based access control, this is when a user account, imagine, has a certain attribute. Let's say they're tier 2 admin. So that's their, well, that'd be a role. Think of attributes kind of like when you log into our website, Trepa Tech. You have a user account, but if we put a little flag on your account that says you've purchased Security Plus, you then get access to Security Plus. If we put a flag on there saying you bought our premium, that means you get access to our flashcards and our dynamic testing environment. Things like that, little attributes that get added. But in here, we're talking about role-based access control, because only access files and systems necessary for their job roles, that's RBAC. Go ahead and pause and read the explanation if you'd like. Question 4. Which of the following best ensures the integrity of a file? So now we're talking about integrity, probably related to the CIA triad or cryptography technologies. When you want to verify integrity, you use hashing, or you could use something like a digital signature, which also uses hashing in conjunction with other things. But that's how we best verify integrity. Not with an encryption, not with data in transit, VPN encryption, and not with access control methods. We verify integrity of a file by hashing it, getting a unique message digest, and then rechecking that file when we want to execute it or look to see if it's been changed. And if we get a different message digest, then yes, that file has been changed. So we will use hashing. Question 5. Which encryption method provides security for a specific section of a storage device, allowing some data to remain unencrypted while protecting a designated area? So imagine like a hard drive. We have a solid state drive. And we just want to, let's say, partition it. Give it a C drive and a D drive. So we give 300 gigs to like the C drive, 200 gigs to the D drive. That's what we want to do. Maybe we're doing a dual boot, whatever the case may be. And out of that 500 gigs, we have 2 separate drives now, 2 separate volumes maybe. That was a way to describe it. And we just want to encrypt one of those partitions. We call that partition encryption, while the rest of it is going to remain unencrypted. Full disk, kind of self-explanatory, it's the full disk. File encryption is the actual specific file, so encrypting a single file on a system. Here it says record encryption protects specific database records, not sections of storage. So just sections of your database that maybe you want protected, you encrypt it. Another method like tokenize, masking a database as well. Moving on. Question 6. Which of the following techniques is used to hide data within an image, audio file, or video so it's not easily detectable? So when we're going to hide something in an image or audio file or video, we call this steganography, okay? Hashing is how we verify integrity. Salting is how we decrease the likelihood of collisions with our hashing, just extra protection for our hashing. And tokenization is when we want to protect like sensitive information in our databases without encryption. Tokenization, masking is kind of that method. So here, this is going to be steganography. So steganography is a data obfuscation technique that hides information within other digital media, such as images, audio, or video files. Question 7. Which of the following security controls is both deterrent and preventative? So we're going to look at security controls, and out of these answers, we want one that's deterrent and preventative. So that's kind of hard. Let's see. I'm going to go with C or D here. Now, a firewall that blocks unauthorized traffic. When you see deterrent, most of the time, this is probably going to be a physical control because, like, yeah, maybe if you post on your website that you're SOC compliant, like that may be a technical way to prove that, like, hey, we've been tested. Our defense in depth is good. So maybe an attacker will be deterred from attacking your your networks. But more than likely, when we hear deterrent, it's going to be something in the physical realm. So a warning sign is a deterrent, but it's not preventative. A biometric authentication system at the entrance of a data center. Now, see, this is where it gets hard. It's like, the definition of deter. Would that deter an attacker? I know if I was attacking and I try to get into a space and I saw a biometric authentication reader, if I'm really motivated and I'm a hacker extraordinaire, right? I've done my social engineering, I somehow got somebody's fingerprints, maybe that wouldn't deter me. Maybe that wouldn't. But it is a preventative method from someone who doesn't have access. Now, a security guard, the human element there, that is a deterrent. Having a security guard will deter attackers saying, hey, no, we got real people there. I'm not going to try to enter this data center. But it could also be preventative as well, because physically another human can stop a human from entering a secure area. So I'm leaning more towards D here. So let's go ahead and, let's click D. And we got that right. Awesome. Pause the video if you'd like to read the explanation. And for this one, I just believe it can be both. Where the biometric authentication system, you don't put that in your compound and say this is deterrent. You just say this is preventative. Where a security guard can be both. It can be detective as well as security guard. Question 8. A company is updating business critical application, a business critical application that has known dependencies on older software components. What is the greatest security risk in this scenario? Okay, so break this down. It's updating a business critical application. Anytime you see the word business critical, we're worried about availability, right? In this specific scenario, we're coming from a for-profit organization, more than likely. It says business critical. So we're like, hey, yes, we're doing cybersecurity, but we need to make sure that this thing stays online, because if we take it down because of one of our updates, even though we know there's vulnerabilities, what's our C-suite going to say? What's our stakeholders going to say if we take something down? Because we're not a revenue generating force in cybersecurity. So always keep that in mind. When I see business critical, I'm always thinking caution. Caution for whatever cybersecurity patch I'm about to apply. So we are updating a business critical application that has dependencies on legacy software here. We're assuming legacy, older software components. So when something is legacy, because that's kind of what we're inferring here, older software, we don't build updates typically with that legacy component in mind. When we're building updates, it's for what would we assume, whatever kind of product this may be, non-legacy dependencies, libraries, whatever the case may be. So we think about the greatest security risk, we think about availability. So let's go through these. The application may require a service restart causing temporary downtime. I wouldn't call that a security risk. That would just be, well, it is if we update it and then it says service restart and we take it down, we mess up our availability. But more than likely in an organization, we would have a maintenance window already like for this before we update, okay? So kind of taking some inference there. The update may take longer than the scheduled maintenance window. That's always a worry, always. But the greatest security risk, we're kind of thinking of security. Employees may need additional training. That's not really what we're concerned about when an update. It's something that's kind of planned into it. And if it's not, rethink how you're rolling out updates to customer-facing or employee-facing things if it's going to change the way they interact with it. The update may not be compatible with legacy applications, leading to security vulnerabilities. So this one kind of, I think, is a little self-explanatory when you see the last bit of the D there, leading to security vulnerabilities. So we're going to go with D. And you can pause the video if you'd like to read the explanation. Let me zoom out a little bit, actually. Some of these explanations get a little bit longer. Okay, question 9. An organization deploys a network of decoy systems designed to lure attackers and analyze their behavior. This deployment is best described as which of the following. So back to our deception technologies. It says a network of decoy systems. So network of decoy systems, we're going to go with HoneyNet. And why are we saying HoneyNet? Because HoneyNet tries to emulate or simulate the actual production network. So a bunch of different systems. Not a single system like a honeypot, not a single file like a honey file, and not a single token like honey token. Question 10. A hospital's patient database must be accessible 24/7, even during system failures or cyber attacks. Which of the following security principles is the highest priority in this scenario? So out of the CIA triad, which kind of is our fundamentals for cybersecurity, when we're applying any sort of measures, compensating, deterrent, detective, preventative control, any control, technical control, anything we do in cybersecurity, it can be related to the CIA triad, what we're applying. And in this case, we're saying that a database must always be available, accessible, available. So this is going to affect the A in that CIA triad, availability. Confidentiality, that's encryption and access control. And integrity, that's hashing, making sure something hasn't been changed. Pause the video if you'd like to read the explanation. Question 11. Which physical security control is specifically designed to prevent vehicles from ramming into restricted areas of the building? So that's bollards. So they're going over physical security. Not much to explain here. Bollards, that's what that is. Those are those big poles that you may see. They may come up from the ground, may be already built stationary. Those prevent vehicles from getting into a certain area. Pause the video if you'd like to read the explanation. Question 12, PKI question. Which of the following best describes the role of a private key in a public key infrastructure system? So when I see private key here, I'm automatically thinking asymmetric cryptography. Because with asymmetric cryptography, we have key pairs that we label public and private. And what you do with one key, you can undo with the other. In cybersecurity terms, if I encrypt with the public key, I decrypt with the private key.
If I encrypt with the private key, I decrypt with the public key. Now, symmetric cryptography, some people may say you have one private key, but CompTIA, the way they describe symmetric cryptography, it's one shared secret key. So looking at our vocab here, being very specific, knowing we're in a CompTIA exam, we're going with private key here. That's going to relate to asymmetric cryptography. So let's look at our options here. It is used to encrypt data that will be decrypted by the corresponding public key. Now, in PKI, using asymmetric cryptography for its intended purpose to, like using Diffie-Hellman to create a shared secret key on our transactions when we're doing like TLS, whatever, that's not how it goes. It's flipped, actually. Typically, the public key will encrypt and the private key will decrypt in PKI. Now, I know if you watch my videos, you're like, well, what about digital signatures? Those are technically maybe a tool, something that's relying on PKI. Now, yes, that's true, but we're just saying specifically in public key infrastructure systems, as in the ability to do TLS web sessions, that's not what a private key is doing, okay? It's decrypting, actually, the public key's encryption, not the other way around. It is shared with anyone? No, it's not true. Who needs to verify digital signatures? No. It is kept secret and used for decryption or signing digital messages. So that is probably going to be our answer. It is kept secret and is used for decryption, which is true. It's decrypting the public key's encryption. And guess what? It also signs digital signatures. That is true because digital signatures, a tool component of PKI that allows us to have non-repudiation and integrity using asymmetric encryption in kind of the reverse order. Private key encrypts, public key decrypts to verify that the sender is actually the one who sent that message that has a digital signature on it. So I'm going to go with C here. The CA does not generate it either. Private key is unique to that web server that's doing that certificate signing request, sending it off to the registered agent, to the certificate authorities. That private key stays local and private, right? So we're going to go with C here. Pause the video if you'd like to read the explanation. Question 13. Which of the following best describes the purpose of accounting in the AAA security framework? So accounting is pretty much auditing. It's logging, seeing who's doing what on our networks. It's logging and tracking activity. So A, ensuring that only authorized users, nope. Tracking user activities and maintaining audit logs. I could probably not read the rest and that'll be the answer, but let's see. Requiring users to provide multiple forms, no, it's authentication. Restricting access to specific users. Based on security policies, no, it's authorization. So we're going to go with B here. Tracking user activities and maintaining audit logs of actions taken on a system. Pause the video if you'd like to read the explanation. Question 14. Which of the following best describes the purpose of version control and security documentation? So version control, that's where we have our major, our minor, our release, and like our beta. So if I go on my MacBook right here, we can just say about this MacBook, here's my version control, right? I'm on Sequoia 15.2. So when I go to 15.3, there's maybe a patch, maybe an update, and that's the numbers we're using. It's sequential. It's a way for us to keep track of our updates and major releases, minor releases, beta, updates, packages, whatever the case may be. So with documentation, it does kind of the same thing, right? We can say, oh, this is documentation for version 15.1 or .0. So let's see our answers here. So when it comes to cybersecurity specifically, we can use version control to say, hey, this is the most up-to-date patch, version, upgrade, current OS, whatever the case may be, and that will be our most secure. So let's look at our answers here. A, to track changes and ensure that the most recent improved version is used. That's probably going to be our answer. To prevent unauthorized users from viewing security documentation, that version control doesn't stop that. To restrict changes, doesn't restrict. To automate the process of applying security patches, no, it's not an automation process. It's just really us assigning a number to, hey, this is our current patch. So we're going to go with A here. I mean, it's more than just assigning a number. It's a lot of like, change control, change management, having a nice, well-oiled machine and CI/CD pipeline. It builds into all that. But if you want to read the explanation, go ahead and pause the video. Question 15. Oh, I got to take a water break real quick. I want to make sure my voice doesn't go away. Okay, question 15. Which of the following best describes the main advantage of symmetric encryption over asymmetric encryption for securing data in transit? We're talking about advantages of symmetric over asymmetric. We're talking about how it uses less compute to encrypt in bulk, or to encrypt in a stream, to encrypt better, right? More efficiently for your compute resources. Compute being your CPU, your processing, your RAM. So, might be going with A here. It doesn't ensure non-repudiation. It eliminates the need for key exchange. That's complete opposite of what it does. It uses 2 keys. No, we're going to go with A here. It requires only 1 key, making it faster and more efficient. Pause the video if you'd like to read the explanation. Question 16. Which encryption method is best suited for protecting an entire hard drive, ensuring that all stored data is encrypted, including operating system files? So an entire hard drive. We need to encrypt an entire hard drive. Have you guys ever heard of BitLocker? This is what that is. Full disk encryption. We're encrypting everything until we boot up, or whatever the case, and then we put in a key, the PIN, the password, and then it decrypts and allows us to use it. The operating system, the stuff in the hard drive. So it's going to go with B, full disk encryption. Pause the video if you'd like to read the explanation. Question 17. An organization installs biometric scanners at the entrance of a data center to restrict access to authorized personnel only. This is an example of which type of security control. This is a good tricky one because you think biometric scanners, there is some technical things behind that. It may be connected to the enterprise, maybe connected to an air-gapped network to an authentication server that has all that data to authenticate based on biometric markers or scanners, fingerprints. But more than likely, we're talking about a physical control here because this is physically stopping someone from entering an area. That's the key in this question. Restrict access to authorized personnel only at an entrance. We're in the physical realm. So we'll go with D here, physical. Pause the video if you'd like to read the explanation. Question 18. A company wants to transition to a zero trust security model. Which of the following principles aligns with the core concept of zero trust? Okay, going over zero trust. So we're going over one of the core concepts here, which is like least privilege, principle of least privilege, always assume breach, and never trust, always verify. It's the 3 of the core principles. I can't think of the NIST standard right now. Maybe in my post edit, I'll throw it up on the screen. But if you go over the NIST standards of zero trust architecture, that's one of those are the 3 core principles. So let's read it. What's inside the network, users and systems are automatically trusted. No. B, users and systems must be continuously verified before accessing resources. So yeah, that is part of zero trust. Never trust, always verify. One of the core principles. Meaning if a subject, whatever that subject may be, service account, user, whatever, wants to access an object, it must always be verified, regardless if it's already been previously verified. So I'm probably going to go with B here. Let's read out other answers. A single authentication check, nope. External users are always untrusted. So that's true. But then it says, while internal users are automatically granted access. That's not true. If this would have said external and internal users are automatically or are always untrusted, we'd have a difficult question here, right, to answer. But we're going to go with B. Users and systems must be continuously verified before accessing resources. Pause the video if you'd like to read the explanation. Question 19. Which of the following security tools is an embedded hardware-based cryptographic module used for secure key storage and system integrity checks in modern devices? This one was hard because of the last sentence. It's going to be B or C. KMS, System Key Management System, that just stores passwords. It's not a secure enclave. B or C is what we're looking at. TPMs are used on motherboards to do integrity checks, like for our secure boots. But HSM does do key storage. And it can also do system integrity checks. I'm leaning more towards C here. But, because it does, let's see, an embedded hardware. Okay, there's our key, embedded. HSMs are typically external. It's an external device. It's an external micro SD in your Android phone. It's external. TPM, that's on the motherboard. So, an embedded hardware-based cryptography module. HSM not really purpose-built for this either, integrity check. So, accurate answer is TPM. I don't really like that one, but it can do secure key storage. It's not completely inaccurate. But pause the video if you'd like to read the explanation. Question 20. Which of the following is the primary purpose of a backout plan in a change management process? Backup plan and change management process. Pretty much that's, hey, before we approve this change you're going to do in our production network, we want to make sure that if something messes up during that, what's our plan to get it back to operational? So backout plan. What is the primary purpose of a backout plan? So again, if you look at our answers here, C is kind of the only one that makes sense because we're saying if something messes up, we need to get back to operational state. So A, to evaluate the business impact. No, that would be a business impact analysis. To define the approved time slot for implementing a security update. No, that's in our maintenance window request. C, to document the steps needed to restore a system to its previous state if a change fails. I'm going to go with C here, but let's read D. To ensure that all changes are reviewed and authorized by the approved stakeholders. That just more describes the actual change management plan and process. Just like overall, that's what it's doing. So we're going to go with C. To document the steps needed to restore a system to its previous state if a change fails. Go ahead and pause the video if you'd like to read the explanation. Question 21. A company is planning to upgrade its firewall firmware. Before proceeding, the security team must analyze the potential consequences of the upgrade on network operations and security. Which of the following business processes does this scenario represent? Potential consequences. I'm going to... So, this part, a company is planning to upgrade its firewall firmware. Okay. Before proceeding, the security team must analyze the potential consequences of the upgrade on the network operations security. All this is describing is the approval process. But what they're doing, what they're asking them to do, like what the security team is actually doing, is an impact analysis. So this one's kind of hard. Which of the following business processes does this scenario represent? I'm thinking we're asking exactly what the security team is doing, not what this overall process is. So I think we're going to go with B, impact analysis. And yes. So overall, that is part of the approval process, but specifically what that security team is doing an impact analysis. Question 22. In the zero trust model, which component is responsible for making real-time access decisions based on security policies? So real-time access, that's going to be our policy engine. So policy administrator will configure that. The policy enforcement point is whatever you have there that's actually like applying something, but the component responsible for making the decision, the real-time access decision, that's going to be the policy engine. Remember, this could be like Active Directory. This could be your domain controller 1, depending on how you do IAM and how you configure your architecture. So we're going to go with B here, the policy engine. So we can look at the description here. Policy engine is responsible for making real-time access decisions based on security policies, user identity, and context, contextual awareness. All right, awesome. Let's move on. Question 23. Which of the following is a primary disadvantage of asymmetric encryption compared to symmetric encryption? So we're going to go with B. It is significantly slower due to complex mathematical computations. Remember, asymmetric encryption, it's really good for our PKI and doing secret key exchange, secure secret key exchange. That's what it's good at. That's what we use it for because of that computational burden, right? Pause the video if you'd like to read the explanation. Question 24. During a scheduled security patch deployment, several critical enterprise applications unexpectedly crashed. The IT team determines that the update required a service restart, but this step was not accounted for in the change plan. What best practice could have prevented this? So essentially, they rolled out a patch, enterprise applications failed. They did their analysis and said, oh, it's because they needed a service restart, which we didn't do during the maintenance window. Or did they even have a maintenance window? So now we're seeing what best practice could have prevented this. It's hard to infer if they even had a maintenance window at all. Well, let's go through our options. So A, conducting a thorough impact analysis to identify service dependencies before applying changes. Yeah, I mean, that's kind of part of it. If I'm going to put out a major patch, I need to know, second, third order effects. I need a backwards plan for that. B, implementing deny lists. No. Scheduling updates outside of business hours to minimize impact. I mean, yes, of course, but that wouldn't prevent they could have had a maintenance window, but if they didn't know about these dependencies, the same thing would have happened. And of course, D, yes, using a maintenance window that allows for system downtime. Yes, but it still would have happened, right? Maintenance windows and approvals would help us not leave us down, but if we go past that window, So we're going to go with A, conducting a thorough impact analysis to identify service dependencies before applying changes. Pause the video if you'd like to read the explanation. Question 25. A security engineer needs to implement a fast, efficient encryption method for encrypting large amounts of data on a corporate server. Which encryption type should they use? So corporate server, it's private, it's internal. We need a lot of encryption. So we need something that doesn't take up a lot of computational resources. So we're going to go with C, symmetric encryption. Question 26. Which of the following best describes the function of a key exchange algorithm? Key exchange algorithm, it's like Diffie-Hellman, elliptic-curve cryptography. Their main goal is to share a secret key, right? Get over that limitation of symmetric cryptography where we have to do like out-of-band key exchanges and then it leaves it vulnerable. With secure key exchange algorithms, it allows us to create a shared secret key between client, server, between a session without having to share that key in an out-of-bound way. So we're going to say it's A. It is used to establish a shared encryption key between two parties over an untrusted network. Pause the video if you'd like to read the explanation. Question 27. Which of the following best describes the primary purpose of digital signatures in cryptographic security? So digital signatures give us integrity, non-repudiation. They verify authenticity. So we're going to go with B here. Ensuring non-repudiation and verifying the authenticity of a message. They do this by using hashing and asymmetric cryptography. Pause the video if you'd like to read the explanation. Question 28. Which security technology provides a protected execution environment that allows sensitive data and cryptographic operations to run separately from the main operating system? So what we're saying here is we're doing cryptography on a dedicated hardware appliance that's not a part of the actual operating system. So I'm leaning towards this is probably going to be HSM, but it could also be Secure Enclave as well. So what's leaning me more towards Secure Enclave is how sensitive data and cryptographic operations run separately. It's not specifically saying that it's another appliance, right? If this is saying which physical appliance provides sensitive data and cryptographic operations to run separate from like a firewall or something like that, I lean more towards HSM. But I'm going to go with Secure Enclave here. So you can see here, a Secure Enclave is a hardware-based isolated execution environment designed to protect sensitive data and cryptographic operations from being accessed by the main operating system or malicious software. Question 29, and yes, it's already answered. I had a little mess up in the recording, so we're just going to go over a couple questions that have already been answered. But question 29, a company needs to encrypt only specific data fields in a customer database, such as social security numbers and credit card details, while leaving other data unencrypted. Which encryption method is the most appropriate? So records in a database need to be encrypted while others are left alone. So that's going to be record encryption. Pause the video if you'd like to read the explanation. Question 30. Which of the following is an example of a honey token? So I already answered it. So again, messed up in recording. It's going to be a fake user credential embedded in a database to detect credential stuffing attacks. So honey token deals with certificates, credentials, unlike honey file, which deals with files, unlike a honey pot, which would be like a single server system VM, and unlike a honey net, which would be an entire network. All those are decoy and deceptive techniques that are meant to give you analysis on potential malicious threats. Okay, now we're back on track without the answer already being up. Question 31. Which key exchange method is commonly used in secure communications to establish a shared secret key over an untrusted network? So essentially what we're asking here is, how do we do secure key exchange to do symmetric encryption? What protocols do we use? So we use asymmetric cryptography to make this happen, but we have specific protocols that do this, like Diffie-Hellman, like elliptic curve cryptography, like, what's that third one? I'll probably, when I edit this video, I'll put it up there. It's like ECDHA. That's really bad. I should know this off the top of my head. But the answer to this is going to be C, Diffie-Hellman, which is a secure exchange protocol. Pause the video if you'd like to read the explanation. Question 32. Which of the following best describes the role of stakeholders in the change management process? So going over change management, stakeholders are really anyone that has a vested interest. Sometimes I used to think of stakeholders as like just a C-suite. That's not true. It's really any person in an organization that has an interest in the organization succeeding. So what best describes the role of stakeholders when it comes to change management? Now, we talk about change management and stakeholders in that exact process. We're probably talking about management and the different approval steps. So more than likely, we're going to go with A here. They review, approve, or reject proposed changes based on their impact on security and business operations. What I always like to point out is business operations too, right? Just because we're technical doesn't mean we forget about the business side of things. Pause the video if you'd like to read the explanation. Question 33. A company implements digital signatures for all employee emails. Which security principle does this primarily support? So digital signatures give us a couple things. They give us non-repudiation and integrity. But when we're attaching a digital signature to our email, that is primarily that's one purpose when we attach it to our email. Now, we can attach digital signatures to not just email, just any message, data, but usually it's to your email. It does give us integrity, but its primary purpose is non-repudiation. That's to make sure that the sender is legit, to make sure that we're kind of authenticating that the sender did actually send this message, and then it also didn't get changed in the process, which would be integrity. But the most correct answer for this question is going to be C, non-repudiation. So again, non-repudiation ensures that an individual cannot deny taking an action, such as sending an email or signing a document. So it's kind of like authenticity, right? Pause the video if you'd like to read the explanation. Question 34. Which cryptographic technique is used to strengthen weak passwords by increasing computational complexity during hashing? So essentially, how do we make hashing stronger? That's what this question is asking. We're going to go with D. That's key stretching. The longer the key, the more secure something is. Pause the video if you'd like to read the explanation. Really say longer, like the bigger size, like 512-bit size compared to a 256-bit size key. The 512 is better. Question 35. Which cryptographic security tool is typically used in enterprise environments to securely generate, store, and manage encryption keys at scale? So a security tool and securely generate and store and manage encryption keys. So remember, TPM is something that's built into like embedded system. It's an embedded thing like on a motherboard. I am thinking hardware security module for this question. And that's because really the store here, store and manage, that's what an HSM is there for. And it's meant to be its own dedicated appliance. So I'm going to go with D, hardware security module. Pause the video if you'd like to read the explanation. Question 36. Which of the following is an example of a compensating control? So think of compensating controls as like you have a legacy server that you can't upgrade, you can't get rid of. So we have to compensate for that risk, for that vulnerability, for that increased attack surface. So a compensating control, it may not completely mitigate a risk, but It helps protect, okay? It helps protect. So let's go through these options. A company without MFA implements a policy requiring complex passwords and frequent password changes. That's probably our answer. And the reason is good IAM security, identity access management security, when we're authenticating identities, authenticating users, is multi-factor. That's really the best way to do it. There's even like the belief out there that passwordless authentication is even better now because it can't be guessed if it's just a push notification on your phone. Like, you can't guess that. You have to have possession of the phone, and then that phone may have 2 factors of authentication on it, right? So to even access the app. So if we can't have that, so there's a risk, there's a vulnerability, what can we do instead? How can we compensate for that? A password policy. So I'm probably going to go with A here, but let's read the rest. A security camera records, that's a detective control. A firewall is configured to block unauthorized access. That's preventative, right? Firewalls prevent things. An organization mandates annual security awareness training for employees. That would be a directive control. More than likely a directive control. So I'm going to go with A here. A company without MFA implements a policy requiring complex passwords and frequent password changes. Pause the video if you'd like to read the explanation. Question 37. An organization wants to strengthen its security posture by preventing unauthorized applications from running on company devices. Which of the following is the most effective solution? So, to increase our defense in depth, we don't want applications installed without prior approval. Sounds like a whitelist to me. This could also be enforcing strict access control, right? We're really, not really access control, just strict download policies. So whitelist is also an allow list. A deny list is a blacklist. The way a whitelist and allow list works is pretty much, there's like an implicit deny, but then we go in and specifically say what applications can be installed. So a lot more secure, a lot more pain when you need to get things approved for like installation on your network. Where a deny list or blacklist is like an implicit allow, and then we have to go in one by one and deny, which takes a lot more time and is a little bit less secure, but grants us the ability to download whatever we want. But here we're worried about our security posture, preventing unauthorized applications. So we're going to go with B here, implementing an allow list that only permits approved applications to run. Pause the video if you'd like to read the explanation. Question 38. A security administrator needs to ensure that encrypted data can be recovered if an employee loses their private key. Which of the following cryptographic solutions is most appropriate? Encrypted data can be recovered in case a private key is lost or stolen. If an employee loses their private key, what do they do? Just delete it? But anyways, definitely not digital signatures, right? It's not going to be digital signature. It has nothing to do with this question. A certificate revocation list actually just it's a server that shows you certificates that are no longer trusted or expired. That doesn't necessarily have to do anything with the private key. And then PKI just describes the entire ecosystem of, HTTPS, right? Of how we have secure connections over the web. It's a lot more complicated than that, but the only good answer here is B, a key escrow. So what is a key escrow? This is a security mechanism that ensures encrypted data can still be accessed if the original encryption key is lost. So pause the video if you'd like to read further on that explanation. Question 39. An organization uses a honeypot to attract attackers and monitor their behavior without exposing critical systems. What type of security control does this represent? So we just want to monitor. So that's detective, okay? It should be detective. It wouldn't be corrective or directive. Yeah, just making sure. Yeah, that's it's just monitor, right? It's in the, I don't want to overthink it. See, what I was just doing was overthinking. That's something you shouldn't do in the exam. Think about it, but don't overthink it. It's there. It's written in plain English, right? No trick questions. Well, CompTIA sometimes. Anyways, question 40. Which of the following physical security measures is most effective for preventing unauthorized tailgating into a secure facility? It used to be called a man trap. Now they call it access control vestibule. It always sounds like I'm saying vegetable, but it's vestibules? Vestibules? Okay, we'll move on. I had a speech impediment as a kid. If you watch my videos, I've said that before. Sometimes words are hard. But yes, that is D. So an access control vestibule is the new man new term for a man trap that prevents tailgating, where we just have two doors essentially that to get through, so you can see if someone's trying to just tailgate behind you. And they typically are monitored as well by like a CCTV. Pause the video if you'd like to read the explanation. Question 41. An IT team implements a new password policy requiring stronger passwords, but they fail to update the organization's security policy documents. Which of the following security risks does this pose? So what happened here? An IT team implements a new password policy that says stronger passwords, but they fail to update the organization's security policy documents. So they implement a policy, but they don't update the documentation. So people don't know about it, essentially, is what they're saying, but they're probably going to be forced, and they may not get a message, right, when they have to reset their password. So what security risk does this pose? Probably A, right, because employees may continue using weaker passwords, reducing security effectiveness. So let me read this. It implements a new password policy. So essentially they're saying we want to do it, but we haven't implemented it. So it's ineffective, right? And why is it ineffective? Because employees may continue using weaker passwords. Okay. Sounds good. Let's continue. Pause the video if you'd like to read the explanation. Question 42. Which of the following is a data plane component in Zero Trust security model? So a data plane component, that's going to be where like the actual bits are coming across. We're actually doing some enforcement, not the control plane where we can see it and we update the policy, right? So what is a data plane component in Zero Trust? Again, that's where it's actually happening. So adaptive identity is just like something we want, right? Something that we'll configure. A policy administrator is in the control plane. That is the person that configures our authentication policies. So policy engine, policy enforcement point is what I would guess, but it's PEP, right? So C, right? So the control plane handles security policy creation and access control decisions, where the data plane actually manages actual traffic flow and enforces it, okay? The policy engine is a control plane component. That one I always get confused. I was thinking, is that representing the data plane? But it's not, right? It's actually a control plane. All right, pause the video if you'd like to read the explanation. Question 43. Which of the following scenarios demonstrates a security risk associated with public key encryption? So, what's a security risk with public key encryption? So remember, a public key in like the public key infrastructure, what it does in asymmetric encryption is it actually encrypts, and then the private key will decrypt. So really the only thing, like if it's revoked, that's not a security risk. If the hacker obtains it, I'm not a hacker, I could obtain someone's public key, that's the whole point. And then D, a public key is stored in a widely accessible certificate repository. Yes, that's the whole point. So the only answer here that makes sense as far as like a security risk is if we lose access to a private key, then we can't decrypt anything. So if we lose the private key for the private key pair for a public key that's doing all this encryption, then we're out of luck, right? We can never decrypt again. If without making new key pairs and then implementing the new key pairs, right? So we're gonna go with C here. Pause the video if you'd like to read the explanation. Question 44. Which of the following best describes the purpose of salting in cryptographic hashing? So salting allows us to avoid things like hash collisions, makes it a little stronger by adding randomization in there. So we're going to probably be, well, it does add randomness as well. Oh wait, I read this completely wrong. It ensures that different inputs always produce the same hash. No, opposite. I don't know what I was reading there. But no, that's not what it does. This is more accurate. It adds randomness to passwords before hashing to protect against rainbow table attacks. Yes, that is one of the things that it does. Pause the video if you'd like to read the explanation. Question 45. A company needs to replace sensitive credit card data in its database with randomly generated, non-sensitive values while maintaining usability for transactions. Which method should be used? So pretty much we have a database full of credit card information that we need to not be exposed, right? So even if it does get exposed, we want non-sensitive data to be in there, non-sensitive values. So someone wouldn't be able to see, like, I don't know what this goes to, what user account, what credit card this belongs to. So we're doing database protection. And the way we're doing it is pretty much replacing it. We're replacing that data with another value that we wouldn't be able to read, we wouldn't be able to understand. So that right there is called tokenization, okay? So explanation, tokenization replaces sensitive data with a random token that has no exploitable value. Pause the video if you'd like to read the explanation. Question 46. After implementing a major network infrastructure change, the security team notices that older network diagrams do not reflect the new configuration. Which of the following is the primary risk of failing to update these diagrams? So not unauthorized users. Really what I see here is that change process didn't happen, so it's not D. It didn't seem like it happened at all. In the proper way, right? Because we would have documentation updates as part of our proper change management. Unauthorized users may gain access to confidential data. Not updating documents doesn't prevent, like, that could happen whether we update or don't update documents, right? So not really related. Employees may not know how to use the updated network. Really, network documentation is kind of more for us, right? The actual IT, the network engineers, the actual professionals. So really that leaves us with only one accurate answer here, and that is security audits and incident response may be hindered due to inaccurate documentation. Pause the video if you'd like to read the explanation. Question 47. Which of the following physical security controls enhances security by detecting unauthorized movement or environmental changes? So detecting unauthorized movement or environmental changes, the only thing that does that in this list is sensors. Pause the video if you'd like to read the explanation. Question 48. A security engineer is choosing an encryption algorithm for secure web communication. They need a strong asymmetric encryption algorithm with a key length of at least 2048 bits. Which of the following is the best choice? So asymmetric encryption on there, RSA, that's the asymmetric encryption option that we have on there. That can go up to like 4096. Pause the video if you'd like to read the explanation. Question 49. Which of the following best describes the role of an open public ledger in blockchain security? So what's secure about the blockchain essentially in a public ledger? It's the decentralization that it has. Pretty much it's all these different nodes in a decentralized computing environment that are verifying whether a hash or a token, whatever is accurate. And as long as we have like 51% in agreement, then we know that our token, our blockchain is accurate. That's a really dumbed down version of it. So with that being said, the most accurate answer here is B. It records transactions in a transparent, immutable, and decentralized manner. It does decentralized authentication. Pause the video if you'd like to read the explanation. All right, here we go. Last question. Let's get it right. Which of the following is an example of a managerial security control? So managerial. So D, that is like technical. A is also more of like a technical, kind of like, yeah, that's a technical control and preventative as well. So that leaves us with B and C. I feel like they're both good answers, but B seems more to me like operational, like we're enforcing this, right? We're enforcing this badge in and out of secure facility due to compliance. This kind of seems more operational. So I really sees the only option we have left, conducting a risk assessment to evaluate potential threats and vulnerabilities. That's something that the managers, the C-suite, people in those positions would want for the organization. All right, we are done. So if you enjoyed this content, please make sure you like, subscribe, share it with your friends, and if you're interested in Security Plus training, click the link in the description below, get access to our live virtual sessions where I'll be teaching it, or one of my great instructors, or our full self-paced course on Udemy, or our custom learning management system, where you can actually access all these questions for life. Thank you for viewing. I'll see you in the next video as we go over Domain 2 questions.